Alright, our new lesson today is what we call the subatomic zoo, and the name zoo is kind of a weird title, but the idea is, if you think of people probably in the old days thought there was only a certain number of animals, and they started discovering more and more animals, so you go to a zoo, you see hundreds of animals instead of just maybe 3 or 4 that you would normally see. So the same sort of thing happens with atomic particles. So we know we originally thought there was electrons, protons, and neutrons, but now we've also added each of those antiparticles, so we've already are up to 6 different particles, so we've now gotten our zoo bigger and bigger. So over time, scientists have discovered that higher and higher energies can actually get the particles to change into something different. And because we get smaller and smaller particles, the forces are actually stronger and stronger, so we have to start using really high energies to be able to break these things apart. So what happens is, if we use 13.6 electron volts, we can get a hydrogen atom to lose an electron. We can remove an electron. At a few hundred volts, we can start to look at different energy levels in the atom and get EMR to emit. Rutherford used about 10 mega electron volts, that's 10 million, to be able to blast an alpha particle at a nucleus and got things to be detected that way. By the time we reach to giga electron volts or billions of volts, we start to see some pretty weird things going on. What happens is once we blast particles with these high energies, we actually get new fundamental particles that were never seen, and they only exist for a split second. So the concept is, a good analogy is, we're throwing a golf ball at a vase to break it, and so normally you'd see, okay, it's just going to break up and we're going to have all these little small pieces of glass, but in the process of it breaking, we get something like a pencil or some other little object that appears just for a split second. So it seems weird, but that's actually what happens when they do this with particles. So it started with cosmic rays. So if you look at this diagram, cosmic ray is basically particles that are emitted from the sun. So we got things like protons and alpha particles, electrons, things like that, but they're mostly protons. You can see about 90% of them, and they're coming in at 10 to the 14 mega electron volts. So this is billions upon billions upon billions of electron volts. So massive amounts of energy, and when they hit our atmosphere, they collide with something like hydrogen or helium or nitrogen or whatever, and those collisions cause these protons to split apart. So you can see in this diagram, they actually split apart into a pion, a positive and a negative, and a neutral. So you can see it actually breaks into 3 different ones for a split second. Then those pions actually split into a muon, and we get some antineutrinos in there, and you can see we get some gamma radiation, and we get another neutron, and we get some electrons, and so on. So we start getting some of these weird chemicals that are particles that exist upon these extreme high energy collisions. And you can see though, but eventually they break down into sort of particles that are more normal. So we get things like electrons and protons and antineutrinos and things like that. So all of these symbols are starting to be identified now as new fundamental particles. So a muon in the picture above, it's sort of they find out it acts like an electron, but it's way more massive. So you end up getting a way larger mass, about 200 times bigger than an electron. And then you also get an anti-muon, which is just be like positive. Pions are just like same sort of thing, but what's weird about pions is you actually get 3 different types. You get a negative, positive, and a neutral, which is kind of weird, and we'll look at those later on. But now, with all these extra particles, we actually get things like over 300 different types. So to keep track of everything, they kind of broke them into different categories based on things like positive and negative and so on, but also on things like how big they are and how they spin. So you can kind of think of these things spinning clockwise or counterclockwise, so that sort of breaks it up. So, and if they spin in whole numbers or half numbers and so on. So what happens is we get, basically scientists have made a chart. So they call them leptons and hadrons. So you can see in the leptons we get electrons, muons, and tauons, and their opposites. And hadrons are broken into mesons and baryons, and you can see the mesons are things like pions, kaons, and so on, quite big objects. And then the baryons are protons, neutrons, and so on. So you can see there's lots of particles listed in here, but that's still not all of them. There's many, many more. If you kind of compare them, you can see in the chart, so an electron, we know it's negative, and you can see that its mass in terms of mega electron volts is 0.511. So if we compare that to a proton, you can see it's positive, and its mass is like 900, so quite a bit larger. So we can do things like look at something like a pion. You can see it's positive, so it's like a proton, but a lot smaller. And we can look at something like a muon, so you can see it's negative, but way bigger than an electron. So you can see they're just sort of comparisons in terms of masses and so on. And we can always convert energy and masses in terms of electron volts and so on. So we got one example. It says let's find the mass of an electron in mega electron volts per c squared. So if we use energy equals mc squared, we can actually solve the mass in terms of energy per c squared. So all we have to do is figure out what that energy of a electron is. So if we take its mass, 9.11, let's actually do it this way. So if we go energy equals mc squared, so our energy would be 9.11 to the negative 31 times 3 to the 8th squared. That gives us an energy of, if we do it in mega electron volts, we get 0.511, which is what the last chart showed us. So if we get 0.51 mega electron volts, that's like 511,000. So roughly 500,000 mega electron volts. So if we kind of take that number as our energy now and solve it for mass, we'd have mass would equal E divided by C squared. So we just take that number, 0.551 mega electron volts, divided by C squared, because that's a constant number anyway. So that's how we can express mass in terms of different units. But Joule still works, but it's just because they're such small objects, it's usually easier to switch them to this kind of unit to be able to compare them a little bit better. And that's it.